Hi folks, this is the last wee video in our study of electric fields then. This is the projectile motion of a charge in a uniform electric field. We can use our linear equations of motion to solve problems on charges that are moving perpendicular to an electric field. It's exactly the same as horizontal projectile motion in Earth's gravitational field. It's what you did in National 5 when you fire a projectile horizontally. A bit like this. Here's a wee blue electron that's being fired from left to right into a uniform electric field. It's experiencing a force downwards. It's being repelled by the top plate, attracted to the bottom plate, and because it's a negative charge, it's moving in the opposite direction to the field lines. The electric field lines always point in the direction that a positive charge would experience a force. So that red electric field vector is showing you upwards, but the electron experiences a force downwards, and because it's moving horizontally at a constant speed, then its horizontal velocity will be constant, its vertical motion will be a constant acceleration, and it will follow a parabolic path. Now note, the motion of a charge moving initially perpendicular in an electric field, then its path will be parabolic, whereas the motion of a charge in a magnetic field will be circular. Remember, in a magnetic field, the force is always perpendicular to the motion of the charge. In an electric field, the force is always in a constant direction. Right, here's our little example then. It's an electron that's fired with a horizontal velocity of 2.7 times 10 to the 7 meters per second into a uniform electric field. And the electron's travelling perpendicular to the field. And we're going to ignore gravity here, so the only force that's at work is the electric force acting on the electron. And we've got quite a few bits and pieces to work out, 3, 6, 9, 10, 11 marks here. I think we'll do this on the iPad and then come back and show you the solutions. Right, here we go. An electron is fired with a horizontal velocity of 2.7 times 10 to the 7 meters per second into this uniform electric field, and the electron's travelling perpendicular to the field, and we can ignore gravitational effects, so the only force that's acting is the electric force, and we have to calculate the time taken for the electron to move through the field. Well, what do we know? We know how fast it's going horizontally, and we know the length of the plates. So let's jot this horizontal information down then. So horizontal speed, 2.7 times 10 to the 7. Horizontal distance it travels is 0.085 meters. And we have to work out the time using the distance speed time equation. Time equals distance over speed, 0.085 over 2.7 times 10 to the 7. And that will give you an answer of 3.2 times 10 to the minus 9 seconds. Very short time because it's travelling very, very fast. Now, A part 2, we have to calculate the vertical acceleration of the electron. Now, it's accelerating because there's an unbalanced force acting on it. That unbalanced force is the electric force. So we're back to our old friend here, Newton's second law, A equals F over m. Now, m's the mass of the electron. We can get that from the data sheet. Mass of the electron is 9.11 times 10 to the minus 31 kilograms. But what about this force? Well, it's the electric force produced by the electric field, and we know that the electric field strength is the force per unit charge. Let's rearrange that. So F equals electric field strength times the charge. And we also know that the potential difference across the plates, that electric field strength is produced by the voltage across the plates, and V equals E times D, the distance between the plates. And we can rearrange that. The electric field strength equals V over D. Now, both of those highlighted relationships are going to be useful to us because we're going to substitute in for F in the A equals F over m equation. If F equals EQ over m and E equals V over D, that will give us VQ over dm we know what all those values are. We know what V is, it's the potential difference across the plate, it's 1900 volts. We know what D is, it's the vertical separation of the plates, 105 millimeters. And we know what Q and M are, the charge and the mass on the electron. We can get both of them from our data sheet. So we're ready to plug all those values into our relationship here and get the acceleration. So let's write it again. A equals VQ over dm, and there is all the values that we've got in the question. 105 millimeters and the mass of the electron. That gives us an answer of 3.2 times 10 to the 15 meters per second squared. It's a really high acceleration, and you can get enormous accelerations in electric fields. So that's what we're looking for, the vertical acceleration of the electron. It was only worth 3 marks. And then part 3, calculate the vertical displacement of the electron at point X. It's like an upside down projectile here. So we have to work out that vertical displacement. Now, vertical displacement. This is an equations of motion question. So we're back to our old friends from higher. It's a two-VAS question. So TUVAS, we know the time that it took to move through the field. We worked that out in part A, 3.2 times 10 to the minus 9 seconds. The initial vertical speed of the electron is 0 because it was only moving horizontally. So vertically its initial speed is 0. We're not interested in its final speed. The acceleration we've also just worked out, 3.2 times 10 to 15 meters per second squared. And it's S that we're interested in. So which of our linear equations of motion are we going to use? We're going to use S equals ut plus a half at squared. And instantly we can get rid of ut because u is equal to 0. So substituting in the other values, we've got a half times the acceleration of 3.2 times 10 to 15 times the time squared, 3.2 times 10 to minus 9. Don't forget to square it. And you do that on your calculator, you'll get 0.016 meters. That's 16 millimeters. That's a pretty tough question. An awful lot of physics in there. Great question. Part B, the potential difference is now increased to 2.4 kilovolts, so the voltage is greater. State whether the electron will leave the field higher, lower, or at the same position as point X, and you must justify your answer. Okay, if you ever get a must justify question, that means you can't have a guess. You have to use some physics to justify why you've put that answer. Now, I'm going to use the relationship we used a wee bit earlier. This one here, A equals VQ over dm. We derived that relationship, but it's going to be useful for us. So let's jot that down again and see if it's useful in our justification and our answer. We're told that the potential difference increases. Everything else stays the same. The only thing that's changing is that the potential difference has gone up. So if V increases, then the acceleration must increase, because Q and D and M are all constant. They're staying the same. And since we used S equals ut plus a half at squared, if A is increased, then S will increase, because the time is also constant, because the horizontal speed of the electron is the same as it was before. That's a lovely question. It's got everything in it. Newton's laws, equations of motion, gravitational fields, electric fields. Cracker. Right, so there's my solutions at the bottom. Slight differences there due to the way that I rounded it. I think 2 significant figures would be better because of the numbers in the question. But that's a typical example of a charged particle moving perpendicular to an electric field and it having a projectile or parabolic path. Last thing then, let's re-mention the unit, the electron volt. It's useful to mention it here because the definition of the electron volt as a unit of energy is that the work that you have to do, or the energy required to move a single electron through a potential difference of 1 volt, is given by the relationship W equals QV. Q will be equal to the charge on the electron, 1.6 times 10 to minus 19. 1 volt gives us an energy of 1.6 times 10 to minus 19 joules. And that unit of energy is called the electron volt. It's a very small unit of energy, and it's widely used in many areas of physics dealing with charged particles. So if you want to convert electron volts to joules, simply multiply by 1.6 times 10 to minus 19. That's it. See you in the next one.